today's session on number theory. Okay, so like initially when you look at it, number theory might like seem very simple. Like it's after all starting with like prime numbers, divisibility, all that things. You've probably studied that in like primary. But the thing is, number theory is anything but simple. It's one of the oldest and richest branches in mathematics. The questions in it go from all the range in puzzles to like problems that take hundreds of years to solve. Like, and we are going to show you the inner workings of number theory today. I want to start with like a brief tour on why we have different number systems from the perspective of say solving equations. So initially, say we have a equation like 2x minus 10 is equal to 6. This is easy to solve, right? The solution is x equal to 8. As in, we have a solution in the positive integers. So that is, this one will give you a solution in say 1, 2, 3, so on. Okay, now that's happy. This thing, real number, natural numbers has good structure. We have solutions to this equation. Say I give you something like x plus 1 equal to 0. This is obviously not solvable using positive integers, but it is solvable. How do we do it? We extend our number system to include negative numbers. So it's like -2, -1, 0, 1, so on. Here we got more numbers and we were able to solve more equations. But what did we lose? We lost some structure in natural numbers. I will mention a word now. We'll explain this later. It's called well ordering. We lose well ordering when we go from positive to negative numbers. Now, negative numbers, yeah, they're also good. They have some structure. But then you can still make equations like 2x plus 2x is equal to 5, obviously. So this one, you again have to extend this to include rational numbers. What do you lose here? Here you lose the sense of discreteness. Like if I asked you how many integers are between -2 and 3, you can tell me the exact number. But now if I ask how many real numbers are there, real numbers, rational numbers, you couldn't tell me. They're like infinite. It's dense in that set. That's what we lose when we go from integers to rational numbers. Then again, even rational numbers are not enough. You can give you something like x squared is equal to 2. Now you need the entirety of the real numbers. What do we lose here? It's a known fact that real numbers are not countable. Certain like we lose certain structure when we gain the power to solve more equations and we lose more structure as we keep going like this. And then finally something like say x1 is equal to -2. We have like the end of this common numbers here systems. Now here we lose order. Like I can't tell you x is less than y in C. It's very useful in like real analysis, real number when you're studying. But when you're using complex numbers, there is no notion of like x is bigger than y. So like whenever you go and increase your like numbers, you lose some structure. Here you lost well ordering, here you lost discreteness, whatever. So in a certain sense, you can say natural numbers has probably the most structure out of all of them. This is why like the things you can prove about natural numbers, they're very vast. They have a lot of like variety. It also makes them significantly more interesting. Okay, so this is the overview of our session today. I will be going over preliminaries. Then Arjun will take divisibility up until modular arithmetic. And then I will come back again for number theoretic functions and a application study of RSA. Okay. So this is our first topic for today. It's called the well ordering. ordering principle. Yeah, this is probably the most important and foundational axiom of number theory. It's you can prove it, but then for now we are going to accept this as an axiom. It simply states that given any non-empty set S, that is a subset of natural numbers, you can always find some element X in S such that for every other element in S, X will be less than or equal to that other element. Now let's look at some like concrete examples. Say the set of all primes. Least element is obviously 2. But then you can also use this in like a, what do you say, more abstract sense while doing proofs. Like if I give you a number A and I give you a number B and I said modulus of A minus B. This is a set of non-empty integers, like modulus of A power n minus B power n. Yeah. This is a set of non-negative integers. I can find like a smallest element in this, even if I don't know what the set exactly is. Like even if I didn't know this, I could, if it's non-empty, I can tell you it's like it has a least element. So okay, fine. This seems very abstract, so I'll prove a small theorem with it so you can get a feel of it. So this is called the Archimedean principle. Given two positive integers a comma b, there exists n such that na is greater than or equal to b. Okay, so let's just think about this in more like before we start the proof. What does this mean? So initially, say I picked like 3 and 2. 3 is obviously greater than 2. We can just do with n equals 1. That's true. Now imagine I gave you like b is like 1,000 and a is 10. What this says is if you add a to itself enough times, it'll be bigger than any possible number. Because like we can take b arbitrarily, right? So how do we prove this? So first we assume for all n, na is actually less than b. Okay. Now what does this mean? This means that b minus na is greater than 0. That is a positive integer. Right? For all n, that is a positive integer. So that means we can make a set S, b minus na, n belongs to n. And since this is for all integers, we obviously the set is non-empty. We can consider the least element in this set, say min s equal to m, which is equal to b minus ka for some k belongs to n. Right. Now, what happens if we consider b minus k plus 1a? This is obviously equal to m minus a, which is less than m. And since k plus 1 is an integer, this must also belong to S. But if it does belong to S, we have that this thing is smaller than m. So I hope you can see the contradiction here. We are telling m is the smallest element, but we find an element in S that's smaller than m. So that means either two things. Either our assumption is false or well ordering is false. Well ordering is true, so our assumption is false. Which means this is a contradiction. That means for some n, at least one n, obviously we know it's infinite because intuition type thing, na is greater than or equal to b. Okay, that's the first proof of the session. If anyone has any doubts, please feel free to put in the chat or raise your hand. We'll unmute you. Okay. Okay, wonderful. Now, this is like the first result that shows you how powerful well ordering is. But like the most useful consequence of well ordering is what we call mathematical induction. Okay, so as I said, well ordering is probably the most fundamental theory of property of natural numbers. Mathematical induction is the most useful property. So what is mathematical induction? So say I told you that some statement P, say P is that n square is greater than or equal to n, right? Assume I told you that P is true for 1. That's obviously true. 1 square is greater than or equal to 1. And then I proved to you that if Pn is true, then Pn plus 1 is true. So you can see like a chain of implications forming here. We know P1 is true. That means P2 is true. That means P3 is true. And you can keep going like this. Mathematical induction says that when you're counting natural numbers like this, like when you prove a statement in this fashion, like if you know P1 is true and then Pn and Pn plus 1 is true, then it has to be true for all integers. Because you can see like the chain, right? 1, 2, 3, so on. This doesn't work for real numbers because they don't have like, this is a consequence of well ordering. Real numbers, we can't well order normally. So yeah, this is the principle of weak induction. Weak induction. It's called weak because the assumptions are weak, not because it's weaker than the other induction. Yeah, there's two inductions. So yeah, we'll solve a question with this. So assume I wanted to find f of n such that it's equal to sum of the first n natural numbers. So that's I run from 1 to n, right? Now we already know this is n into n plus 1 by 2. Ignore that for now. Assume we don't know. So we have f of 1 is equal to 1. F of 2 is equal to 3. F of 4 is equal, f of 3 is equal to 6. Now, how would you do induction here? Like maybe you can make an educated guess that Pn is equal to Pn, the statement Pn. Pn is a statement here. That's very important. Pn is not a function. Pn is just a statement about the number n itself. Pn is that f of n is equal to n into n plus 1 by 2. Assume you got this by like looking at the numbers, seeing a pattern. Now you want to prove this pattern. That is one of the main powers of induction. If you know something is true for a couple numbers and you know how to extend it, then it is true for all numbers. So how would we do that? Yeah. So we think of, yeah. So we have P of 1 is true. Now what is the next thing we need? We need to prove that P of 1 is true means P of n plus 1 is true. We need to prove that. How do we do that? So assume P of n is true. That means f of n is equal to n into n plus 1 by 2 is equal to 1 plus 2 plus 3 plus so on into n. Now f of n plus 1, which is equal to 1 plus 2 plus 3 so on up to n plus n plus 1. So this thing is just f of n. So we can substitute this back in here. We'll get n into n plus 1 by 2 plus n plus 1. That is n plus 2 into n plus 1 by 2. Now you see that this is the same formula when you substitute n is equal to n plus 1. So what we proved here is P of n is true, then P of n plus 1 is true. So by this chain reasoning, we get that by weak induction, this formula always holds. Now, how would you go about proving weak induction? So assume you had some statement you wanted to prove, Pn, and we know that P1 is true, P1 is true, comma, Pn implies Pn plus 1. Okay, yeah, that was our basic assumptions of weak induction. Now assume, take a contradiction. Assume Pn is false, use M, Pn is false for some M belongs to natural numbers. Now what we can do is, we can make a set of those. It's called as S. This is M such that P of M is false. Now from our assumption, we know this is non-empty, right? And so we can find the minimum of S, min S. Let's call this K. So we know Pk is false. Pk is false. Now I want you to think about, what about K minus 1? K minus 1. Now this argument you have to listen to very carefully, right? If K minus 1 belongs to S, if K minus 1 belongs to S, then this is a contradiction. That is the first thing. If K minus 1 belongs to S, that is a contradiction. If K minus 1 doesn't belong to S, from our this thing, conditions for weak induction, we know if K minus 1 doesn't belong to X, it must imply that Pk minus 1 is true. Because if it was false, it would belong to S. That is what it doesn't belong to that set means. But if Pk minus 1 is true, that means Pk is true. That is again a contradiction. So either scenario, you get a contradiction here. That means it's false, right? Any doubts about the proof? You can put in the chat, raise hand, whatever is fine. Okay, right. So now I want you to think about induction as dominoes. You make the first one fall, everything falls. That is the way. You prove that the first one falls, and then you prove that anything falling will hit the thing in front of it. That is induction, at least the weak induction. We'll discuss one more problem in weak induction. It's another function only, g of n, which is equal to 1 plus r square plus r power n minus 1. Normal or geometric series, right? Same thing for weak induction we do. G of 1 is equal to 1, true. G of n plus 1 will be equal to g of n plus r to the power n minus 1. Now assume P of n is that g of n is equal to r power n minus 1 by r minus 1. So you want to substitute that here. You get r power n minus 1, r minus 1 plus r power n minus 1, which is equal to r power n plus 1, no, r power n, yeah, this is plus 1, r power n plus 1, r power n plus 1 minus 1 by r power n. So yeah, that was a bit fast, but then like this was just to show that it does work, right? Now we talk about the other type of induction. We call this strong induction. We start with the same thing. P of 1 is true, but here we use like the full strength of P of 1, P of 2 up until P of n is true. then P of n plus 1 is true. You can see how this is stronger, right? You need more conditions for this to happen. They are logically equivalent, of course, because like P of 1 is true means P of 2 is true. P of 2 is true means P of whatever n is true. Like if weak induction were to hold, this would be true either way. They're both logically equivalent. There's no difference logically between them. The only difference is in the things that need to, like say, we need to prove for it to work. Now, why would you want to use strong induction would be one question. This is, consider this series, right? 1, 3, 4, 7, 11, so on. This is a form of Fibonacci series, not like the normal one, but then it's like 1 plus 3, 4, 3 plus 4, 7, 4 plus 7, 11. Right. Now I want to prove something. Let's call this an. So this is a0, a0, yeah, a0, so a0, a1, a2, a3, so on. Right. I'll call this a1, a1, a2, a3, a4. What I want to prove is an is less than or equal to 7 by 4 power n. Right. If you people have a pen and paper with you, I'd encourage giving it a try. Like it'll be better for you to like solve proofs yourselves without me telling it. So yeah, P of 1 is obviously true. 1 is less than or equal to 7 by 4. Now, how do you prove P of n plus 1? By assuming P of n minus 1, so on up until P of 1. Right? P of n plus 1, an plus 1. Now, as we discussed before, an plus 1 is an plus an minus 1. Right? Now, from these two assumptions, we know that this is less than or equal to 7 by 4 power n plus 7 by 4 power n minus 1. Right? That's less than or equal to 7 by 4 power n minus 1 into 11 by 4. Now, 11 by 4 is less than 7 by 4 whole square. So we can just put it here. 7 by 4 to the power of n plus 1. I'm hoping you can like check if this is true, if you need to. So yeah, you see how weak induction would not have worked here. We needed to know for an and an minus 1, then only this would have worked. I mean, technically we didn't need all of this, but then this is just strong induction. Sometimes you need the power of everything behind you to also like help to prove the next statement. Now the proof of strong induction is similar only. You take that set S, M such that PM is false. It means that false. This means that 1, 2 up until M minus 1 does not belong to S. Same argument as before. I think that's fine. Any questions, doubts? I have one last thing to prove before we are done with induction. Yeah. If anyone wants to volunteer a stab at how to prove this. Oh, yeah, sure. Which part? The proof of strong induction. Okay. So yeah. So you take the k is the minimum of this. K is equal to minimum of s. That means every number less than k does not belong to us. That means p of 1, p of 2, p of k minus 1 is true. So from strong induction, p of k is true, and that's contradiction. Okay, cool. Yeah. Anyone wants to take a stab at proving this? I mean, it is induction, yeah. Still, I'll give you like a minute. Brownie points in assignment. Yeah, I forgot to tell. Brownie points in assignment for anyone who can tell me how to do this with induction. Assignment is very hard, bro. Telling you. You need brownie points. Fuck off. Don't make me sad now. Anything? Fine, light iron only proof. No brownie points for you people, bro. So P of 1, we have 1 plus A less than or equal to 1 plus A.
I'm sorry. Wait. Ishit wants to try.
Crazy, bro. Yeah, and anyone else can also try, right? It's not just Rishon. I can give you a hint. Yeah, you can do it with weak induction. I have given a hint on the screen. Okay, that's the proof. Okay, so I'll walk you through this. So what we did is we wrote n plus 1. We split that into n and 1 plus a. We know n is true from our argument of our weak induction. So we have this. We have this, and then 1 plus a is just positive, so you can multiply it on side. Oh damn, bro, he actually wrote a proof. Yeah, seems legit. I think. Seems legit. Brownie points for each other. Nice. Other way, so you have this extra n a square term that's positive. You can remove, and then you'll get another less than sign. Okay, wonderful. Now we go to a topic. Okay, I just want to discuss some basic binomial theorem here. Nothing too crazy, like just enough for like it to be good in. You'll probably need it later for like modular arithmetic and shit. So like binomial theorem. First thing, I'm hoping all of you know what factorial is. This is our symbol for NCK. This is n factorial, k factorial, n minus k factorial. We'll be using this notation extensively. It's easy to write. Yeah. So what is binomial theorem? Binomial theorem, as I assume most of you know, x plus y power n is equal to sigma k runs from 0 to 1, nk x bar k, right? X bar k, y power n minus k. Yeah. Easy enough. Now we can prove this using induction. So first we need the Pascal's rule, nk plus nk minus 1 is equal to n plus 1 by k. This you can prove using simple algebra. K factorial n minus k factorial plus n factorial k minus 1 factorial n minus k plus 1 factorial. So you can take n factorial k minus 1 factorial and n minus k factorial common. Then this is 1 by k plus 1 by n minus k plus 1. Adding both of those, we get n factorial k minus 1 factorial. Yeah, Amal, that is correct. N minus k factorial. Yeah. This would be n minus n plus 1 by k into n minus k plus 1, which comes out to n plus 1 factorial by k factorial n minus k plus 1 factorial. Right? This is our n plus 1 ck. Right? That's our Pascal's identity. That's the reason the entity of Pascal's triangle exists. Now I'm going to sneak one more integration here. We're going to prove the binomial theorem using integration. That seems easy. So x plus y power 1 is equal to x plus y. Easy. Now we assume x plus y power n is equal to sigma nk x power k y power n minus k. We want to prove for the next one. So we multiply x plus y on both sides. So that would be x plus y power n is equal to sigma n by k x to the power of k plus 1 to the power n minus k plus this would be x to the power k by the power of n minus k plus 1. I hope you can see how this is related to like the Pascal's identity. You see that, right? It's you're getting a somewhat like similar thing to show up. That's like very important in mathematics. That's seeing that there's some similarity between two things. Proving it is similar is a bit harder, but then seeing it is more important. So what do we want to do here? Yeah, we can split this into two. K runs from 0 to n, nk x to the power of k plus 1 to the power of n minus k plus k runs from 0 to 1 x to the power k y to the power n minus k plus 1. Okay. Now we are going to shift indices. We are going to push k k to like k is equal to, what do we want to do this? K is equal to k dash minus 1. So k dash runs from 1 to n plus 1 n by k minus 1 and here this will be k dash and y to the power n minus k dash plus 1. And here again you do the same thing, but here you set k dash is equal to k minus k dash is equal to k minus 1. K is equal to k dash plus 1. K is equal to k dash plus 1. Oh no, just leave it like that. It's fine, right? Yeah, just leave it like this. Be n minus k here, n k x power k by the power n minus k plus 1. Okay. Yeah. So now you bring these two together. Like for k dash equal to k equal to 0, k dash equal to 0, you'll have a term from this. So you'll have, it'll be like this: n 0, x of 0, y of n plus 1 plus. Now here, now this is from 1 to n because both the indices are there. You'll get simply Pascal's identity. So n plus 1 to the power k, x power k, y power n plus 1 minus k. And in the last term will also be outside, will be like this: n x power n, y power it's n plus 1. Yep, that's the n plus 1 term from here. N plus 1, so k is n, plus 1, yeah, and then y is 0. Y is 0, right? N plus 1 to the power, wait, plus 1. Bring it together, you get k comes from 0 to 1, n plus 1 power k. Like this, you can read it as n plus 1 by n. This one, get it some jugaad somewhere. N term, s to the power k by the power n minus k plus 1. Okay, that's just proof of binomial theorem by induction. That's not insanely useful here, just for like another thing for induction. Now we're going to take attendance, so please everyone put your name on the chart. We'll take like 2 minutes for attendance. Please put your name on the chart. It's important for like certificate things. Yeah, anyone has any doubts, anything, feel free to like raise your hand or something. I felt a bit fast, so like, anyone has any doubts, please go ahead. You can ask. Otherwise, we'll start. Arjun will start at divisibility once attendance is done. I will wait for 1 more minute in case anyone forgot. Okay, if everyone has put attendance, we'll begin session again. Okay.
Hello. Hello, guys. So I'm Arjun, and this is the second session in summer school, and I'll be teaching you all divisibility and modular arithmetic. Um, yeah, and I'll focus a bit on proofs because I feel that is important, and proofs help us develop a sense of direction and thinking. So this part of the session will be heavy on proofs. Yeah. And if you have any doubts at some point, please interrupt me. Yeah, and I'll ask some questions also. And yeah, try to unmute and answer for those questions. Yes. So we'll start with divisibility. So divisibility is the notion that like you can represent one number as an integer multiple of others. So basically, you write that A divides B. So this literally means A divides B, right? Um, Basically, it means that B by A is an integer. So naturally, uh, as a consequence of this, you can't divide something by zero. So you assume that A is not equal to zero. And similarly, you can also say that if B is zero, B by A is zero for any A that is not zero, right? Because zero is an integer. So every single integer divides zero. So this is the basic notion of divisibility. So for just to state a few examples, you can say that 2 divides 4, 3 divides 12, and so on. Yeah. Now we come to something called the division algorithm. So it's a way to represent uh, an integer in terms of like a linear multiple of the other integer. So this is just a fancy way of stating something we've already learned in lower classes. So we all know the formula that dividend is equal to quotient into divisor plus remainder. So this formula is just a fancy way of stating this theorem. The theorem is just a fancy way of stating this formula. So basically, it states that for given any two integers a and b, you have two unique integers q and r such that a is qb plus r. So we will prove the uniqueness and the existence of such a thing using the well ordering principle that Swami taught you all. So basically, it's for example, let's say you have a is equal to 6 and b is equal to 3, right? No, let's say b is equal to 4, right? You write 6 is equal to 4 into 1 plus 2, right? So your a is 6, your b is 4, and q is equal to 1, and r is equal to 2. So you can note that uh, you can't write 6 in terms of 4 in any other way. Like yeah, also under the condition that 0 less than r, 0 less than equal to r less than equal to b. So this is a very important condition, 0 less than r less than equal to b. So this is actually what uh, is the uh, foundation point to prove that uh, such a representation is unique, right? Yeah. So now note that let's say you want to write like 6 is equal to 4 into 2 minus 2. Okay. This is also a valid representation, but the problem is here r is equal to minus 2, which does not satisfy our constraint. So this is simply wrong. So now let's actually start proving that something like this exists, right? Yeah. So we'll do it case by case. So first assume first the case where a is equal to 0, right? So if a is equal to 0, uh, you basically write 0 is equal to 0 into q plus plus r, where r is also 0, right? So for any b belongs to any integer, right? If a is equal to 0, you can just write 0 is equal to q plus r. For the case where, yeah, so you can just write that q and r are 0, and this is unique, like as you can see, because if you increase r, it is not possible to write b into q, right? Uh, let's take the other case where a is greater than 0, and yeah, b is greater than 0, right? So now we'll define the set S of Rn, where Rn is equal to a minus nb, and it being greater than or equal to 0, right? So this is all positive values of a minus nb, where n is an integer, right? Yeah, so now we say that R naught is the minimum of S. So this is, yeah, you can see that this is a discrete set. So by the well ordering principle, uh, there exists a particular R naught, which is the minimum of Z, and it is greater than or equal to 0, right? So now yeah, now let's prove that this is indeed the like there does exist a minimum, right? So let's say Ri is equal to a minus ib, right? So you get that a is equal to Ri plus ib. Now note that R of I plus 1 is equal to a minus I plus 1 I plus 1 into b, and this is Ri minus b, right? So for the case, so yeah, so we know that there exists a particular R naught, right? And we prove that R naught is less than or equal to b using this, right? So now note that Ri plus 1 is Ri minus b, and this if this is greater than 0, so we'll basically prove it by contradiction, right? So if Ri plus 1 is greater than 0, then Ri plus 1 belongs to S, right? And Ri plus 1 is less than Ri, because you're clearly subtracting b and it is positive, like this is that, right? So this is less than Ri. So if Ri plus 1 is positive, then Ri plus 1 belongs to the set, and Ri plus 1 is less than Ri. So this implies Ri plus 1 is the minimum of S, right? Which is clearly a contradiction. So basically, yeah. So basically, we get that from here. We go to the fact that Ri plus 1 is less than 0, which implies Ri minus b is less than 0, which implies Ri is again less than b. Yeah, so that is one part of the the inequality. And let's prove the uniqueness of some uniqueness of this. So let's assume that a is equal to b. Yeah, so uniqueness basically means that a is equal to bq plus r. A comma b are two integers, and q comma r are also two integers. So it basically means that there exists only one pair, q comma r, such that this representation is possible with 0 less than equal to r less than equal to b. So let us assume that there exists two pairs, right? So let's assume a is equal to q1b plus r1, and it's also equal to q2b plus r2, Both of the, so q1, q2, r1, r2, all of them being integers, and r1 comma r2 both being less than, this is not less than equal to, both being less than, and less than b and greater than or equal to 0, right? Now you get that b times q1 minus q2 is equal to r2 minus r1, right? So this implies that uh, b divides r2 minus r1. Why? Because q1 minus q2 is equal to r2 minus r1 by b, and this is an integer. So r2 minus r1 is divisible by b, and we have also assumed that b is greater than 0. So we don't have any problems when we are dividing, right? Yeah, so note that uh, r2 and r1, r2 and r1 are both in this range, right? So what could be the maximum possible value of r2 minus r1? So let's just list the possibilities. R2 minus r1, let's say the possible values is a set of integers, right? So the minimum possible value will obviously be, let's say r2 is 0, and r1 is minus of b minus 1, so minus b plus 1. So this will be the minimum possible value. So yeah, and some other possible values would be, let's say, like 1, sorry, minus 1, and 0 and 1. So can anyone tell me what the maximum possible value in this set will be? So what's the maximum possible value of um, r2 minus r1? Either put it in chat or like just b minus 1. Yes, that's correct. So the maximum possible value of r2 minus r1 is b minus 1. So a notion in divisibility. So let's say uh, b divides something. Let's say uh, b divides some integer capital. So it's clear that um, capital P has to be greater than or equal to b, at least the absolute value, right? Because if you write if you write the integer multiples of b, right? So what are the integer multiples of b? You have like something like, let's say you have 0, you have b, you have minus b, minus 2b, so on, 2b, and so on, right? So if you can notice that the absolute value of all of these, except for 0, right? Except for 0, the absolute value of all of these is greater than b itself, right? And yeah, the maximum possible absolute value achievable in this set is uh, b minus 1, right, at these two extremes. So it's clear that none of the elements other than 0 are not divisible by b here, right? So if b divides r2 minus r1, so if b divides r2 minus r1, then r2 minus r1 has to be 0, right? Then r2 minus r1 has to be 0. So you get that now you get from here that uh, b into q1 minus q2 is equal to 0, right? And you have assumed that b is greater than 0, right? So this implies q1 minus q2 is equal to 0. So essentially now you proved that r1 is equal to r2 and q1 is equal to q2. So you assumed that there are two different solutions and ended up proving that they are the same solution. So this is a proof for the uniqueness of the division algorithm. So there exists only like one solution which satisfies this thing. A is equal to qb plus r such that 0 less than equal to or less than. Yeah. Now let's move on to something called the Bizout's identity. Uh, yeah, I hope all of you are familiar with what a GCD is. GCD is just the greatest common divisor. Oh, also, um, we didn't prove this theorem for the yeah. So we didn't prove it for the case where you can have a less than zero and b greater than zero, etc. So all of them are kind of the same thing, right? Uh, if you want, I can prove it, but it's almost exactly the same. It's the same proof, basically. Yeah. So Bezout's identity states that for any two integers a comma b with GCD of a comma b being b. So what GCD of a comma b is that largest integer that divides both a and b. So for example, GCD of 3 and 6 will be 3. Yeah, GCD of 3 and 6 will be 3, and GCD of, let's say, um, 12 and 36 will be 12, and GCD of 7 and 9 will be 1, because 1 is the largest integer that divides 7 and 9. So 2, 3, 4, so on, they don't divide any of the numbers. Yeah. Though they don't divide both the numbers. Yeah, so basically it states that for two a comma b which are known, there exist two integers x and y such that you can write d is equal to ax plus by. Okay, so d is equal to ax plus by. One important point to make note here is that the theorem doesn't state that x comma y is unique. Right? So in the previous theorem, the division algorithm, we proved that a pair q comma r is unique. But in the Bezout's identity, there's no explicit statement that x and y are unique, because there in fact exist infinitely many such representations, right? So yeah, let's prove that you can write the divisor as a linear combination of the two numbers, right? So yeah, so let's say you have GCD of a comma b is equal to d. So this implies that d divides a and d divides b. I hope you all are understanding the notation. So if you have an issue at any point, uh, yeah, just put a message. Yeah. So a consequence of this is that, yeah. So let's say you write a is equal to d a dash and b is equal to d b dash. So is there anything you can conclude about b dash and b dash and a dash? So basically, what you get is that GCD of a dash comma b dash will be 1, right? Because I'll tell you why. Or does someone want it?
If it is not one, then we can bring that common factor and make GCD of a comma b as d times that common factor.
Yeah, so he's right. So basically, what he's saying is that if we'll prove it by contradiction again, right? We'll prove it by something called contradiction, where you assume something to be true and you prove it is not. So your assumption itself is false. Uh, yeah. So if GCD of a dash comma b dash is some k which is greater than 1, then a is equal to d times k a double dash, and b is equal to d times k b double dash, where a double dash and b double dash are some integers. So from here you get that dk divides a comma b and dk greater than d, because k is greater than 1, right? So this contradicts our entire assumption of like the statement itself, right? It's not anymore the greatest common divisor, right? So that is why this is wrong. Like this is not possible. So a dash and b dash are indeed prime. So we in a way we start from the so yeah. So essentially you are stating that you can write d is equal to ax plus by, and you can write it as a times k a dash plus b times k b dash. Oh sorry, it's d. No wait. Oh sorry, x times d a dash plus y times db dash. Right. Essentially just remove a d, so you get a dash x plus b dash y. Now you can note that this is in fact a kind of the same it's kind of the same statement of the theorem itself, because gcd of a dash comma b dash is 1, and that is indeed what you have here. You have gcd of a dash comma b dash. So does anyone want to take an attempt at proving this? Fine, I'll just go on with it. So basically again you can just construct the set s is ax plus by, right, for x comma y being integers, right, and also assume that ax plus by greater than 0, so just the positive multiples, right? So by the well ordering principle, so just the positive multiples, also note that down. By the well ordering principle, there exists a minimum of s, so let's call that m, right? So we know that um, m divides both a and b, right? Yeah, because it is a, so yeah, let's just write the division algorithm again, right? So a is equal to some qm plus r. Let's say q1 m1 plus r1 and q2 m plus r2, right? And you also know that s is of the form ax plus by. So basically you m is of the form ax plus by. So you basically you get q1 times ax plus by plus r1, which you can write it as a times q1 q1x plus q1 by plus r1. So now basically you need to prove that this is kind of a multiple of a. So we said that uh, what you can write is the GCD. So what will be the minimum element here will actually be the GCD itself, right? So can you think of why that could be the minimum element? So if there is something less than uh, the GCD itself, right, then again it divides both A and B, and the moment you subtract one of them, right, you can see that that will also be a part of the set. So that is kind of a contradiction, right? So we say that this is indeed the GCD of a comma b, and it exists in the set, right? So basically you proved that um, GCD of a dash comma b dash exists in the set ax plus by, where ax plus by is greater than 0 for some x comma y belongs to integers. So yeah, uh, this is the proof that this writing of two numbers is actually possible. So for example, you can say, let's say you get 7 and 9 as I talked about. So the GCD is 1. Right? So you can write 1 is 7 into 3 plus 9 into 7 into 4 plus 9 into minus 3. You can also write um, 7 into minus 5 plus 9 into 4. So there are actually infinitely many representations of this. Uh, a very simple proof is that, let's say you just do 1 is equal to 7 into minus 5 plus 9 into 4 plus 63 minus 63. Right? You can just write 7 into, just say 7 into 63 n minus 63, where n is a positive integer. You can just write 7 into minus 5 plus 9n plus 9 into 4 minus 7. So this is just a direct construction of the fact that there are infinitely such possible representations of 1 as a linear combination of 7 and 9. Yeah. So now let's talk about something called the Euclid's algorithm. So this is not the usual Euclid's algorithm. So I'll put a star here. So the usual Euclid's algorithm goes like A is equal to uh, B Q naught plus R naught, and then you talk in terms of uh, like Q naught is equal to some other, like, yeah, let's just not confuse ourselves with that. So that in essential is the original Euclidean algorithm in essential is uh, a repeated application of the division algorithm. So this is slightly different. So yeah, basically this theorem states that if GCD of a comma b is equal to some, let's say, k, or just d, right? If GCD of a comma b is equal to d, basically that is equal to GCD of a minus b comma b, which is also GCD of a comma b minus a, GCD of a plus b comma b, and so on. Yeah. So you can see that if you keep applying this, it kind of goes to GCD of a minus kb and b, and GCD of a comma b minus k, and so on. So let us prove this. Yeah. So yeah, again we start with the same setup. So assume that GCD of a comma b is equal to d. You have that d divides a and b, and that uh, if a is equal to d a dash and b is equal to d b dash, then GCD of a dash comma b dash is 1. So we have proved this, or rather just stated this in the previous proof. So here, yeah, here we proved why a dash and b dash are co-prime, why a dash and b dash are co-prime. Yeah, co-prime is just a word for the GCD being 1. So 7 and 9 are co-prime. Yeah. So yeah, let's carry on. So basically we have to prove that a minus b. So we have that we want to prove that GCD of a minus b comma b is equal to GCD of a comma b. Right? So what it kind of boils down is that we have a minus b is equal to d times a dash minus b dash, and b is just d times b dash. So we need to prove that a dash minus b dash and b dash are coprime. Because if they are not, then you can write d is equal to k a double dash minus b double dash. So no, we'll just write some, some k naught. Just assume that k naught is a dash minus b dash and d times k b double dash. So again, uh, this is this contradicts the fact that uh, d itself is their divisor. D is the greatest common divisor. So this is kind of what we need to prove, right? Yeah, and given a dash comma b dash is equal to 1. So yeah, GCD of a dash comma b dash um, is equal to 1. So assume, so we'll again go by the proof by contradiction. Yeah, so assume the GCD of a dash minus b dash is actually greater than 1. So basically there exists some k which belongs to the positive integers, set of positive integers, and k is greater than 1 such that k divides a, no sorry, k divides b dash and k divides a dash minus b dash. Right. So basically, you can also write this also like implies in a way that k divides a dash minus um. Okay, wait, just a second. I'll just yeah. So basically, this means that you can write a dash minus b dash is equal to n times k, right? And you can write b dash is equal to some n naught times k. So you have a dash minus n naught k is equal to nk, right? Sorry, yeah, you have a dash n naught k is equal to nk. Now you just add, some like let's say, mm, let's just add some multiples of b here. So some nb into b dash, right? So you have, sorry, let's just subtract a multiple of b dash. Yeah. So you basically have a dash minus b dash into 1 plus n naught is also, some integer times k. So you have that k divides a dash minus nb dash as well, right? So this implies that k also divides a dash. Can someone say why? Yeah, fine. So I'll just move on here. So basically, I'll just explain once again. We have k divides b dash, which implies b dash is b naught times k, right? This, and you also have k divides a dash minus b dash. So you have that k divides this, right? So it is kind of outside the equation now, right? So in a sense that a dash is equal to, yeah. So you basically you can write a dash is equal to some nk plus b dash, and you know this thing, right? So you basically a dash becomes k times b naught plus n, where this is now an integer. And so note that k divides a dash and k divides b dash, right? So and k is greater than 1, right? So this implies GCD of a dash comma b dash is actually greater than 1. So it's at least k, right? Greater than or equal to k. So this contradicts our fact that a dash and b dash are co-prime, right? So this is wrong. So this implies that a dash minus b dash and b dash are indeed co-prime. So it proceeds the same way for uh, the other way around also, like a dash and b dash minus a dash and so forth. So a dash and a dash minus 2b dash. So now we'll solve a problem. So this is in fact the first ever IMO problem. So for people who don't know, IMO is the International Math Olympiad, probably the most uh, prestigious high school math competition. Yeah, so I'll just state the question. Okay. So we have to prove that 21n plus 3 by 14n plus 2, 21n plus 4, 21n plus 4 by 14n plus 3 is irreducible for every natural number n. So what an irreducible fraction is, basically let's say you have 8 by 4, right? No, that's not a good example. Let's say you have 3 by 9. You can write it as 1 by 3. So this is not irreducible because you can kind of simplify the fraction into yeah, SRMs is also a precision solution. So you can simplify the expression into a simpler fraction. So this is not irreducible. Something that's irreducible will be, let's say for example, 7 by 9. I don't know why I keep using 7 and 9, but yeah, 7 by 9 is an irreducible fraction. So can anyone say what is it that we need to prove to say that the fraction is irreducible? So like, in what case would a fraction be irreducible? Like, what would be the relation between the numerator and denominator? Yeah. So basically, you need to prove that GCD of 21n plus 4 and 14n plus 3 is equal to 1. So we will go about proving this by this theorem. So yeah, we'll go about proving this by this theorem. So let's do the first application. Let's subtract this from this. So yeah, so let's subtract this from this. So basically GCD of 21n plus 4 minus 14n plus 3 comma 14n plus 3. So this is just a minus b. This is b. This is a. And so you'll get this to be GCD of 7n plus 1 and 14n plus 3. Now assume this is some c and some d, right? So write GCD of 7n plus 1, 14n plus 3 minus 7n plus 1. So this is c and this is c. This is d minus. This will get GCD of 7n plus 1 and 7n plus 2. So let's say this is E and F. This is just GCD of 7n plus 1 and 7n plus 2 minus 7n plus 1. So this is E and this is F minus E. You get GCD of 7n plus 1 and 1. So if you are doing the GCD of some number and 1, the largest integer that divides both the number itself and 1 is 1, right? So this is just 1. So this means that you can't divide the numerator and denominator by any number other than 1, so you can't simplify it. So yeah, so this is the proof for the question. It's also a neat proof. So we all have heard many times that consecutive integers are co-prime, right? Consecutive, let's say natural numbers are co-prime. 6 and 7, their GCD is 1. 8 and 9, their GCD is also 1. So it kind of can be proved by this theorem, which, because let's say you have GCD of n comma n plus 1. You just do one application of this and it becomes GCD of n comma 1, which will be 1 itself, right? So this is kind of a proof of the fact that consecutive natural numbers are covariant. So now we'll actually move on to something called modular arithmetic. So modular arithmetic, so far, when discussing divisibility, we were concerned about, so yeah, we have a is equal to bn plus, say, bq plus r. So in divisibility, we were concerned about both q and r, right? But in modular arithmetic, we are only concerned about r. So we don't have anything to do with q. So r is the thing that really matters in modular arithmetic. So the basic statement in modular arithmetic is that a is congruent to b modulo n. So this is how you write it. So this, you pronounce this as a is congruent to b modulo n. And what this means is that, so you can see that the statement here is, it's written here. So basically, yeah, first of all, it's defined for integers, right? So we are not going to use something like a is 4.8, b is 1.2 or something. All of them are integers. So throughout the session, assume that unless or otherwise stated, a comma b are always integers, and n, whenever we are using, n is a positive integer. So yeah, it's defined for integers a and b and some n which is non-zero. So because again I stated, uh, you can't really state divisibility of 0 because you can't divide anything by 0. So yeah, so what this statement basically states is that if this is what is written, it implies n divides a minus b. So it's as simple as that. N divides a minus b. So it defines a notion of uh, describing numbers with respect to divisibility and remainders. So we're not cared about what the quotient is, just um, you know, we're just wondering about what the remainder is with respect to two integers a comma. So for example, 4 is congruent to 1 mod 3 because 3 divides 4 minus 1. You can also notice that 4 is congruent to, let's say, 7 mod 3 because 4 also, sorry, 3 also divides 4 minus 7, which is minus 3. So again, this thing, let's say this is, yeah, so let's say a is congruent to b mod n. B is not unique. B is not unique. There are in fact infinitely many representations of B. So let's just prove it again. So let's say n divides a minus b. It implies a minus b is some nk where k belongs to a set of integers. Yeah, need not be positive integers, it can be set of integers. So you get that a is some b plus nk. So there are in fact like, or you can also in a way write that b is equal to a minus nk. So since k is any integer, there are in fact infinitely many b congruent to the same modulo a for some particular n. So some more examples. 7 is congruent to 2 mod 5 because 5 divides 7 mod 7 minus 2. So yeah. So let's discuss some basic properties of uh, modular arithmetic, and before that, yeah, just something about symbols. So yeah, so this implies that, this states that a implies b. So if a is true, B is true. This, on the other hand, let's say let's call it a double implies, right? So it is like A if and only if B, or for short, A if IFFB. So basically, what it means is that if A is true, B is true. If B is true, then A is also true. So this is a two-way relationship. Right? So this symbol, it represents a two-way relationship. So yeah, so some basic properties. Yeah, we'll also be proving each of the properties. So the first one, A is congruent to A mod n. Why? Because n divides 0. So n divides A minus A. So A is congruent to A mod n. Right? Yeah. And then the second thing. So A is congruent to B mod n implies, sorry, this is not implies, if and only if B is congruent to A mod n. So let's say this is true. We'll prove it one way. So this implies that n divides A minus B, right? So let's multiply minus 1. So this implies n divides A minus B times minus 1 also. So it means n divides B minus A also. Now from here you can write that B is congruent to A mod n, right? And you can also prove it the other way around. Let's say n divides B minus A, multiply it by minus 1, and you get the other thing also. Yeah, the next property is if A is congruent to B mod n and C is congruent to D mod n, then A plus B is congruent to C plus D mod n, right? So yeah, so from here you have that n divides A minus B and n divides C minus D. So you can write B is yeah, you can write B as, let's say, n1A, no, some, what do I write? Yeah, some k1n plus A. No, wait. You can write A as some k1n plus B and C as k2n plus D, right? So A plus B is essentially what is A plus B? Yeah, k1 times n plus B. Oh, sorry. This is A plus C is congruent to B plus D. Yeah, no, it makes sense. K2 times n plus D, right? This is equal to n times K1 plus K2 plus B plus D. So note that, let's say this is some T. T minus B plus D is equal to n times K1 plus K2. So n divides T minus B plus D. This implies T is congruent to B plus D mod n. So our T is just A plus C. So A plus C is congruent to B plus D mod n. Right. So, yeah. Now the second part of this, that AC is congruent to BD mod n. Right. So just assume the same thing. So we write this as K1 times n plus B and K2 times n plus D, and this is equal to n square K1 K2 plus n K1 D plus nk2b plus bd. Now you write this as n times nk1 k2 plus k1d plus k2b plus bd. So this implies that, let's say this is t minus bd is equal to n times something. So n divides t minus bd. So t is congruent to bd mod n, and t is essentially AC. So AC is congruent to bd mod n. Right? Yeah, the last part is it's yeah. So you have to prove that if A is congruent to B mod n, then A per k is equal to B per k. So can someone say like what we apply to get this? Which so it's essentially just applying the previous theorem twice. So you have A is congruent to B mod n and A is congruent to B mod n as well. So assume this is like this is C and D, right? So you have A square congruent to B square mod n. Yeah, again, A is a positive integer, right? And you can do the same. You can keep on doing the same thing. A square B square mod n. You have A congruent to B, same thing. So A cube B cube, right? And you can keep on doing the same thing. So that's why if A is congruent to B mod n, then any A power k is congruent to B power k mod n. So yeah. You can also see that it's like it's also a cool way to observe that n divides A power k minus B power k, and then also divides A minus B. So generally we have learned that A minus B always divides A power k minus B power k, right? So if n divides A minus B, which in turn divides A power k minus B power k, it's only natural that n divides A power k minus B power k as well by transitivity. So yeah, moving on. Oh yeah, a question. So please attempt this question. One. Let me. Okay, yeah, you all are right. So basically, observe that from 4 factorial onwards, right? There is this is 4 into 3 factorial, right? So clearly 4 divides 4 factorial. Yeah, so another thing, if let's say if n divides a, right, then a is congruent to 0 mod n, because a minus 0 is divisible by n. So yeah, notice that from this onwards you can write everything as 5 into 4 factorial plus 6 into 5 into 4 factorial and so on. So every term henceforth is divisible by 4. So it leaves a remainder of 0 on division by 4. So what you need to care about is just the first 3 terms. So 1 plus 2 plus 6. So this is 9. And 9 leaves a remainder of 1 when divided by 4. So that is how we get that the remainder as well. Yes. Yeah. So some other theorems which are also as important. So note, yeah, the first one is just that if you have some CA being congruent to CB mod n, and the GCD of the C and N is let's say some D, then A is congruent to B mod. Yeah, so I think it's better I just like write it down instead of stating. Yeah, wait, sorry. Yeah, so no, let's take an example. So let's say C is equal to 2 and n is equal to 6. And let's say a is equal to 4 and b is equal to let's say 21. Fine. No, let's b will be 19. Yeah. So yeah, so note that 8 is congruent to 38 mod 6. This is in fact true because 6 divides 8 minus 38. So this is true. So now what the theorem states is that 8 is congruent to 38 mod 3, right? This is also in fact true because 3 divides 8 minus 38. So why 3? So the GCD of c comma n is equal to GCD of 2 comma 6, which is 3. No, sorry, which is 2. Let's call it D. So this theorem states that CA is congruent to, sorry. Oh yeah, so this should be, I think, A and B. So this will be 4 is congruent to 19. So this is also in fact true because this is minus 50. So yeah, this theorem basically says A is congruent, basically states that A is congruent to B when you take mod of n by d. So it's an effective way to reduce your numbers. Let's say you're dealing with large numbers, so like let's say you can C can be as large as let's say 2000 and n is 4000. Then you can essentially come to mod 2. So can like it's a great way to simplify. So yeah, we can prove it. So yeah, so let's say CA is congruent to CB mod n, right? This is the statement. So this implies n divides CA minus CB, uh, which means n divides C into A minus B. So now let's say GCD of n comma C is equal to D. So just write this as dn dash, or in fact dn by D divides C, no sorry, let's say nc dash into A minus B. So no, yeah, you can just, sorry, this will be D. You can just cancel out this D because it contributes in both of them, right? And also note that this is essentially n dash and this is c dash. N dash and c dash are co-prime, right? So clearly n dash doesn't divide c dash. It just doesn't divide. So you get that n by d should divide a minus b. And what this means is that a is congruent to b mod n by d. Yeah, so that's how you prove this. And let's now look at the second theorem that's stated there. So wait, I added the wrong page. Yeah, so fine. So this is dealing with polynomial representation. So if A is congruent to B mod n, then P of A is congruent to P of B mod n for some, let's say P is an integer polynomial, right? So a polynomial with integer coefficients, right? So how, yeah, so let's see how. So let's say P of X is A naught plus A1 x bar, A1 x bar 1 plus so on till an x bar n, right? So A naught is congruent to A naught. Wait, I'll just write it here. A naught is congruent to A naught mod n. Okay. So simply the fact that A is congruent to A naught. Now, A1 is also congruent to A1 mod n. And since we have that A is congruent to B mod n, A1 into A is congruent to A1 into B mod n. Similarly, A2 into A square is congruent to B2 into, sorry, A2 into B square mod n. And this keeps going till an A power n is congruent to bn B power n mod n. Now you can just add all these up, or like you can just add it one by one also. You can add here, add here, add here, so on. So the right side essentially becomes a0 plus a1 into a plus a2 into a square plus so on, a n a power n, and left side becomes again a0 plus a1 b plus a2 b square and so on. So essentially this is p of a and this is p of b. So if you have a polynomial also, you can define a divisibility or modulo in terms of that polynomial, right? So yeah, now let's move on to something called Chinese remainder theorem, which is like very important and a very cool theorem, right? So it states that if you have let's say some k positive and co-prime integers, and you define a congruent system like x is congruent to a1 mod n, x is congruent to a2 mod n2. So it states that this has a unique solution model like congruent modulo n1 and n2. So basically, let's say you have all this, right? So let's say the solution for this is x is equal to x, right? So this will actually have infinitely many solutions, right? So how? So let's say x is one solution. So you just add n1, n2, n3, so on up to nk, right? So this new x dash. So this x dash will again be a solution to this set of equations, right? So this has unique solutions. This has, sorry, infinitely many solutions. But what it states is that let's say solution x is congruent to some let's say x naught mod n1, n2, so on up to nk, right? Then it states that you can't have basically x is congruent to like x1 mod so on up to nk. So if this is true, then x1 has to be equal to x0, right? You can't have x1 not equal to x0. Like this is not possible. So that is what this theorem states. So basically, uh, this is unique. So uh, so far we proved things using like uh, proper like what do I say? Yeah, like assumptions and proofings. So we'll try a different style for this one. So let's do something called construction. So essentially, we'll give you the solution for x. So, like we will find out what x is. We'll find it out, right? So yeah. So let's say capital N is n1, n2, n3, so on up to nk, right? And define so ni as n by ni. So essentially n1, n2, so on up to n minus I minus 1 into ni plus 1, so on up to n. So define ni like this, right? And also, yeah, it is known that GCD of ni comma nj is 1 for I not equal to j, right? Yeah, so by Bezos theorem, right, which we discussed earlier, we have that, yeah, also note that uh, ni and ni are also co-prime. Why? Because ni is co-prime to all of these terms, right? Like this and the entirety of that is co-prime, right? So you can write 1 is equal to some x ni plus y ni. right? Because the GCD is 1, this representation is possible for xy being integers, right? So we define the construction. So we define the construction x is equal to sum of um, ai, xi, ni, I running from 1 to k. So ai is just this, and xi is this. So write as xi and yi, right? Xi is that, and ni is what we have defined here. So this is the construction, right? So basically, we need to prove that x is congruent to ai mod ni. So just write x as this thing, like the entire thing itself. So you have essentially a1, x1, n1, a2, x2, n2, so on, ai, xi, ni, x2, so on up to ak, xk. And now note that other than this term, right, in every this will be capital N, right? In every, let's say, nj, where j is not equal to I, you have an I in it, right? So it will be like n1, so on up to ni. Let's say j is greater than I, right? nj minus 1, nj plus 1, so on up to nk. So ni divides nj for I not equal to j, right? So when you talk about, let's say, congruences, you can remove all these terms. So x is congruent to ai, xi, ni mod ni, because ni divides n1, n2, and nk. So everything except n capital Ni will be divided by small ni. So now you write this as ai into 1 minus yi ni, right? This will be equivalent to ai minus ai yi ni mod n. So again, note that you have ni here. So this essentially is congruent to 0 mod ni. So you get x is congruent to ai mod. So this is in fact a very valid construction for the Chinese remainder theorem, right? Yeah. So if anyone has any doubts, you can ask now, and we just move on to some other theorems next. Fine. So you all might have seen these problems in like math competitions and all that. Find 2 power 3000, let's say one. Find the remainder when this is divided by, like, let's say 5, or like many types of these problems. So usually we try to solve these things using the two theorems mentioned here. So these are very fundamental and very useful theorems. More than fundamental, they are highly useful. Um, so yeah, the first one is called Little Fermat's theorem. So this is something that Pierre Fermat stated. So basically, if you have two integers a and p, p being prime, with their GCD being 1, then a power p minus 1 is congruent to 1 mod p. So yeah, for example, let's say p is 5 and a is, let's say, 9. No, let's go with the simpler number. Let's say a is 7. No, let's say a is 6, right? So 6 power 4 minus 1 is 6 power 5 minus 1 is 6 power 4, which is 1296. So 1296 is equal to 1295 plus 1. This being divisible by 5, right? So like 1296 minus 1, 5 divides that. So 1296 is congruent to 1 mod 4. So 6 power 5 6 power 5 minus 1 is congruent to 1 mod 4. This is an example of the theorem. So we'll now in fact prove this theorem, right? So yeah, so you have now, let's say a to a 3a and so on up to p minus 1 into a, right? Now each of these is congruent to ri mod p, let's say, right? So now I'll define something called a residue class, right? A residue class. So this is essentially the set of all reminders when you divide by p, right? So it will be 0, 1, so on up to p minus 1. Set of reminders when division by p, right? So note that yeah, since a is co-prime to p, I'm saying that all of these will correspond to a unique ri, right? So a unique ri mod p. Why? So let's say for example, let's say so yeah, we already have that a is co-prime to b. So let's say we have a is congruent to r mod p, and let's say 2a is also congruent to r mod p, right? So you can subtract this, right? So you get that a is congruent to 0 mod p, right? So this is kind of not possible because this implies that p divides a, which contradicts our assumption that GCD of a comma p is 1, right? So yeah, let's say even if r here is not 0, it still implies that p divides a, which is like just not possible, right? So this can be like anything. So this can be like some ka, and it can be like some, let's say ma, and this can be na. So this will be like n minus m, and yeah, n minus m will always be like less than p, right? So n minus m will be in between 0 and p, assuming n is greater than m, right? So it'll always be between 0 to p minus 1, and yeah, like basically we are trying to prove that it'll be between 1, it'll be like from 1 to p minus 1. So none of these is divisible by p, right? So we can remove this basically, and it'll still imply that a is congruent to 0 mod p. So yeah, this is violating the fact that GCD of a comma p is 1. So basically, let's say a is congruent to some r. Let's say a is congruent to r1 mod p. 2a is congruent to r2 mod p. So on. Basically, we are saying that ri is not equal to rj for I not equal to j. So all of them have a unique residue modulo p, right? So now just multiply all of them. So just do a into 2a into 3a so on up to p minus 1 into a is equal to, is or rather congruent to, you have r1 r2 so on up to rp minus 1 mod p. Now note that um, every every possible residue will be covered here other than 0, because the moment you have division by 0, like the moment you have that uh, let's say some a into k is congruent to 0 mod p, K is obviously less than 1 because you're only covering those multiples. So P doesn't divide this, but P will divide A, right? So so it is never possible that A into some K is congruent to 0 mod P. So everything from 1 to so on up to P minus 1 will be covered here because all of them are unique. So and you are putting P minus 1 of them. So all of those will be covered. So you basically get uh, P minus 1 factorial into A power P minus 1 is congruent to P minus 1 factorial mod P. Now, uh, P minus 1 factorial and P are co-prime, right? Because P doesn't divide any of the integers less than P itself. These two are co-prime. So you can essentially just cancel these out. Or like basically you have that P divides you have P divides P minus 1 factorial minus A power P minus 1 into P minus 1 factorial. Take this common. Since P doesn't divide this, P should divide 1 minus A power P minus 1, and this implies A power P minus 1 is congruent to 1 mod P. So that is how you prove this theorem, right? So yeah, that's a simple proof of a little Fermat's little theorem, and yeah, the main thing to focus on here is the thing called residue class, right? Yeah, and does anyone have any idea like how you can prove Wilson's theorem? It's like pretty much the same thing, right? So like anyone can put in chat how how you can approach the proof of Wilson's theorem. Fine. Like I'll just prove it, I guess. So it kind of follows the same thing, right? That each of them have like a unique residue, like modulo this, right? So when you have like when you multiply all of them, so 1 up to P minus 1, each of these oh wait one second. Yeah, so actually I might have to teach you all something called inverses, but fine. Yeah, we'll come back to this after. Like if we have time, I'll prove this because this involves teaching something called inverses. So yeah, I'll come back to that. So yeah, for now we just say that this is like assume. So like P minus 1 factorial is congruent to minus 1 mod P. So for example, let's say you have again P is 5. Note that um, 5 minus 1 factorial is equal to 4 factorial is 24, and that is congruent to minus 1 mod 5. So why minus 1 is because 24 minus minus 1 is 25 and 5 divides 25, right? So yeah, and yeah, if anyone has any doubts at this point, please ask me because we'll be moving to something that's new. Yeah, so now we'll talk about something called a Pell's equation and also about something called continued fractions. So we all have like seen these rational approximations for like different um, different constants like pi. So like for example 22 by 7 is an approximation for pi. You also have some like better approximations like for example there's I think 313 by something. One second. um, This is so like one approximation of pi is 22 by 7. Some better approximations are like 2, I think 223 by 17. Yeah, 223 by 71 is in fact a better approximation for pi. And you also have 333 by 106. 333 by 106 is an even better approximation for pi. Right. So yeah, so this is yes, this is what we are going to discuss in this. So we'll find approximations for not just pi, but in fact things like root 7, root 3, so rational approximations that just get better and better. So uh, something that we're not going to discuss here that's beyond the scope is that for things like root 3, right, there's no best rational approximation. So because if you have a certain best rational approximation, you can always better it, right? Like you can always go one up and kind of bring it closer to the number you're trying to do. So like the more number of iterations we do, the better or the more accurate we get, the closer we get to our actual number, right? Oh yeah, sorry. So yeah, mostly I just be writing in this part, right? So yeah, let's define a notion of uh, a continued fraction, right? So a continued fraction is basically something you write of the form, let's say 2 plus 1 by 1 plus 3 by 1 plus 4 by 1 plus 5 and so on. This is what a continued fraction is, right? So you have various steps in this fraction and you have something that is a leading number, right? So yeah, how you represent this is generally by something called like by a bracket notation, right? So essentially, like you will write this fraction as, let's say this is equal to s. S will be written as 2 comma yeah, so you basically like oh wait, sorry, I made a mistake. You write as 1 by 3 plus 1 by 4 plus 1 by, let's say, 5 plus so on, right? So this will always be 1. So yeah, so you write it as 2 comma 3 comma 4 comma 5 and so on, right? And sometimes you also have the case where the fraction tends to repeat. So you have 2 plus 1 by, let's say, 3 plus 1 by 3 plus 1 by 3 and so on. So let's say this is some s dash. S dash will be 2 comma 3 bar because 3 just keeps on repeating, right? So that is how you write a continued fraction. And what is so good about a continued fraction is that so s obviously here it keeps on going, right? So it is it's not a rational number, right? Because if it's a rational number, um, because it's a rational number, oh yeah, yeah, fine, we can give a break now. Just a second. Because if it's a rational number, then the expansion of that has to terminate at some point, right? But this is clearly a non-terminating, like this is in fact endless, right? So if you have an infinite continued fraction, then it's not a rational number. And the deeper you go into the fraction, the more closer it is to the number itself. So yeah, we'll put one short break now and we'll come back and like find like better approximations and we'll discuss the Pell's equations.
Okay, we'll take a 3-minute break. You guys can like drink water, like yeah. Any doubts here you can ask. The attendance will be taken, I think, later, not now. Or now. Okay, fine. Yeah. You guys can have a 3 minute break, like go drink water or something. Yeah, guys. If any doubts you have, now is a good time. Like small doubts, we can clarify like verbally only, or you can put it in the chat. Anything works. Any doubts in the session up until now? Like after this, it will get slightly harder. So it's important that you are aware of the concepts.
So I think we can come back. Right. Yeah. So Hemant asked how to prove that such a fraction in fact converges. Right. So basically, yeah, let's say you have something like 2 plus 1 plus 3, so on. So a rule or a rule of thumb when writing such a fraction is that let's say this is some s dash, right? This will tend to be the floor function of s dash or the greatest integer function of s dash, and this will be the fractional part. So this will be like s dash minus s dash, or simply you can write as s dash. And because you do 1 by something as the fractional part, this in itself will be greater than 1, and it's kind of a way where how you can like continue, writing the fraction. So why it terminates, uh, just do 2 by 1 plus 3 plus 1, right? Like this will be like uh, yeah, this will be less than 2 plus 1 by 3 plus some fractional part, right? So this terminates, so this has to terminate, right? Like you can't have something be infinity when something greater than it is, like this is clearly this is what. So like 1 by 4, right? So 9 by 4 is greater than this infinite fraction or like continued fraction, so it clearly terminates. So yeah, that's how you prove that it terminates. So yeah, now we'll see how to in fact write a continued fraction, right? So as I said, you generally write it as the floor or the greatest integer function of that plus the fractional part. So we'll do an example. So let's say you have root 3, right? So the greatest integer function of root 3 is 1, and the fractional part of root 3 will just be root 3 minus 1. So you just write root 3 is equal to 1 plus root 3 minus 1. Now you write this as 1 plus 1 by yeah. So how to write 1 by that thing? So just um, rationalize the function essentially. So just do root 3 minus 1 into root 3 plus 1 by root 3 plus 1. So this becomes 1 plus, this will be root 3 squared minus 1 squared. So 2 by root 3 plus 1. And now you take that to the denominator. So it becomes 1 plus 1 by root 3 plus 1 by 2. Right? So now you treat this part as another thing. So you just carry on from there right now. Right? So ignore all this and carry on from this. So let's say this is like T1. So root 3 plus 1 by 2 is approximately 1.73. 2.73 by 2, which is approximately 1.36, I think. Yeah, 1.365. So yeah, it's approximately this. So the greatest integer function of T1 is just 1, I think. Is it 1? Yeah, it's 1. And the fractional part of T1 is root 3 minus 1 by 2, right? So yeah, you just do 1 plus 1 by 1 plus root 3 minus 1 by 2. Now you write this again as, yeah, so you rationalize that as well. 1 plus 1 by 2, 2 by root 3 plus 1, I think. So this will cancel out. So this again becomes 1 plus 1 by 1 plus 1 by root 3 plus 1. Right? Wait, is it root 3? Yeah, it's root 3 plus 1. So now just focus on this. Since this is T2. So the greatest integer function of T2 is 2, and the fractional part of root 3 minus 1. So you get 1 plus 1 by 1 plus 1 by 2 plus root 3 minus 1. And again, do the same thing here. 1 plus 1 by 1 plus 1 by 2 plus 1 by root 3 plus 1. And here 2 will come. So notice that at one point we were here. So where exactly? Just a second. So yeah, at this point we were already there, and we have kind of come back here, right? So essentially the fraction just keeps repeating from here on. So it's like 1 plus 1 by 1 plus 1 by 2 plus 1 by 1 plus 1 by 2 plus so on. So you can kind of write this to be 1 comma 1 2 bar, because this repeats in units of 1 and 2. So yeah, this is the continued fraction expansion of root 3. And I'll tell you why this is useful right now, right? So let's say we'll evaluate the fraction itself, like until only like the first few convergence, right? So let's say first, like without doing anything, you have first one, or rather just let's just go to the first one, right? So you have 1 plus 1 by 1. This is 2. Let's say you go to the next stage, 1 plus 1 by 1 plus 1 by 2. This becomes 1 plus 2 by 3, which is 1.66. Now let's say you go to the next stage. Wait, 1 plus, yeah, this is 5 by 3, sorry. My bad. Which is 1.66. Now let's go to the next stage. 1 plus, so 1 plus 1 by 2 plus, I think 1 by 1, right? So this becomes 1 plus 1 by 3, 4 by 3. This becomes 7 by 4, which is 1.75. Let's say you go one further. So you do 1 plus 1 by 1 plus 2 plus 1 by 1 plus 1 by 2. This becomes 2 by 2, 2 by 3. Mm, 3 by 8. This becomes 19 by 8, I think. So what's 19 by 8? 19 by 8 is 2.38. No, it's not 19 by 8. It should be something else. 2 by 3. 2 plus 2 by 3. So this is okay. Yeah, this is 19 by 11. Sorry, this is 19 by 11. So 19 by 11 is 1.7272. So if you note that you have 2 first, which is around yeah, root 3 is 1.732, so on. So you have 2 first, which is around how much is it off from root 3? So it's off by around, let's say, how much? Around 0.26, right? And later you have 1.66, which is off by around 0.06. And then you have 1.75, which is off by 0.02. And then you have 1.72, which is off by 0.01. So with each successive addition of a level, our approximation just keeps getting better. So 19 by 11 is a very close approximation to root 3. And if you add another level, you get even closer, right? This is why continued fractions are useful. And now we'll discuss something called the Pell's equation. So The Pell's equation is essentially just any equation of the form, a Diophantine equation of the form x square minus ny square is equal to 1. And let's say x square minus dy square is equal to 1, where d is not a perfect square. Okay. And I'll discuss why this is useful. So let us say, yeah, and it has been proved that there are infinitely many solutions for this. So it's proved that it has infinite solutions, right? So let's say xi comma yi is a solution for this Diophantine equation. So you have xi squared minus yi squared into d is equal to 1, which implies uh, xi squared minus 1 by yi squared is equal to d, and root d will get us this. And basically this implies root d is root d is equal to root of xi squared by yi squared minus 1 by yi squared. Now let's assume yi is much greater than 1. Then this implies root d is approximately root of xi by yi squared. So this becomes this just becomes xi by yi, right? So since you know that there are infinitely many solutions, there is no actually like large solution. So the larger the solution in terms of x and y, so the larger the y, the better the approximation is for root d, right? So let's just discuss the case of d is 3, right? So x square minus 3 y square is equal to 1. So let's just look at our convergence here. So we have 7 by 4, right? So if you look at here, let's say you set x as 7 and y as 4, you have 49 minus 3 into 16 is 49 minus 48, which is 0, right? Note that 7 by 4, 7 comma 4 is a solution for the Diophantine equation or the Pell's equation, and it is also a good rational approximator for root 3, right? We can also check for 19 by 11. So 19 square is, I think, so it's not necessary that all the solutions will be a part of the continued fraction expansion, but uh, all the solutions are good rational approximation. So 19 square is 361, and yeah, I think it's clear already that this is not satisfying the Pell's equation, but it is still a solution, like it is still a good rational approximation, right? So it's 363, right? So it's again, it's like almost close. Like you get x square minus 3y square is, I think, minus 2. So it's very close to the solution, in fact, right? So let's say you find a bigger solution to this, right? Let's say you get something like, what could be some other solutions? Wait, I'll just Google this up because I don't know. I can't pull this out of my head. Yeah, so mm, okay. I can't really find some. Fine. So let's say you find a bigger solution in terms of x and y, then that just gives you a better rational approximation for root d itself, right? So you can also try it out for like other uh, like irrational roots like root 7, root 5, root 11, root 9, and other things. So yeah, that kind of concludes my part. Now Swami will carry on with number theoretic functions. Yeah. So if you have any doubts, you can ask me.
Yeah, if you have any doubts, ask and put your names in the chat box for second round of attendance. We wait for like 2 minutes for all of you to put.
Fine, I'll stop sharing.
Okay, I hope you all finish your attendance. I'll be starting again. Okay, so some functions in number theory have special importance. Yeah, like obviously every branch of mathematics has some like important functions. Here we'll deal with functions that are from n to n, like from natural numbers to natural numbers. We'll call them number theoretic functions. In general, though, like normally they can be from natural numbers to anything, but for this session, we'll consider only natural to natural. Okay. Now, then we'll start with like what do you say? Function that seems rather intuitive. The number and sum of divisors. Those are two different functions. They're like usually very easy to analyze. So this is tau, which is the number of divisors, and sigma, the sum of divisors. Yeah, simple enough definitions. Let's try finding values for some, for say 12. Tau 12. We have, I'll write the divisors on top. We have 1, 2, 3, 4, 6, 12. So that's 6 of them. So tau 12 is 6. What about sigma 12? That would be 1 plus 2 plus 3 plus 4 plus 6 plus 12. 3, 6, 10, 16. That's 28. Right? Easy enough to calculate. These are rather simple functions. Now I want to introduce some new notation here. So this summation d divides n. This is summation over divisors of n. So then tau 12 would tau n would simply be written as dn1, right? So the number of divisors, that many times you add 1. Sigma n would be dnd, right? Makes sense, right? Wonderful. Now, like I want to make an important point here that's like will be important for this entire session. Say some number n, you write as p1 power k1, p2 power k2, so on pn power kn, right? All the factors of n will be in form p1 a1, p2 a2, so on pn an. Actually, this will be the okay, and then each a will be less than or equal to k1 and less than or equal to 1. I'm not going to prove this statement. It's pretty intuitive. So I hope you can agree with me. Each factor of them will just have every prime factor, and it will be the exponent of that will be at most the one in the actual number, and at least, oh, wait, this is 0. Excuse me. And yeah, obviously P1 to P1, P2 are all distinct primes. Distinct primes. That's just the prime factorization, right? That's the prime factorization of n. Okay, good. Now, how many factors are there? We'll use like a combinatorial argument to find tau of n. If we can write n as P1, K1, P2, K2, PR, KR, every D will be distinct up to the choice of AI. Like here for P1, I can choose from 0 to Ki, any K1, I can pick any number, right? And then for P2, again, I can pick from 0 to K2, so on. So it's independent choices for each exponent. So it's 1 plus K1 into 1 plus K2 into 1 plus Kr. That is tau n. Okay. Any doubts you can ask? We're using a combinatorial argument to find tau n. Okay, and we can do a sanity check here. We know tau 12 is equal to 6. 12 is 3 into 2 square. That'll be 1 plus 1. 1 plus 2 equals 6. Makes sense, right? Okay. Now I'm going to prove that tau is a, okay, no, I'm not going to, okay. Tau is a multiplicative function. Here, very important point. When I mean multiplicative in the context of number theory, I mean number theoretically multiplicative. That is, Fmn is equal to Fm, Fn, if and only if GCD of m comma n is 1. This is a more nuanced definition of multiplicativity I'll be using for the entire section now, right? It's multiplicative only if both the numbers are co-prime. Like, okay, so if you consider like tau n is equal to like n is equal to p1 power k1, p2 power k2, so on, pr power kr. What does it mean if some number m is co-prime to this? That means none of its prime factors are common. Like no qi, it's there. G1. No, wait. None of these factors are common. So when you multiply them, you have P1, K1, Q1, A1, so on, so on. All of these are still distinct. So tau n would simply be 1 plus K1, 1 plus K2, so on, into 1 plus A1, 1 plus A2, so on. Right? You can accept that, right? If you have any problems, any issues with that, please put it in the chat. Okay. Great. So we have a closed form. So I'll just recap in short what we did here. We had tau n. We found closed form. And then we use that to prove it's number theoretically multiplicative. That's what we did here in a small recap. Now, the other function we were looking at was sigma n, right? Like assume if n was a prime number, say sigma p, what all factors does it have? 1 and p. How about some prime power? I would have 1 plus p square whole plus p power k, right? Now, if we consider something like q into p power k, where q is prime and q not equal to p. So they are co-prime, right? Different prime number. What are the factors of this? First of all of these factors will be there, right? and then you'll also have the factors, the other, like you have one extra prime, right? So then you'll have factors like this, q plus pq plus p square q plus so on p power kq, right? Now we can do a sanity check here. This is k plus 1 factors, this is k plus 1 factors, tau of q into p power k, 1 plus 1 into k plus 1 into 2k plus 2, right? That's how many we have. So we counted all of them. Now if you look at this, you can take q common out from here, right? And then you can write this as sigma q into p power k is equal to 1 plus q into 1 plus p power k, right? So you can see that, like, by looking at this, you would feel like it's multiplicative. Now, how can we prove that it is multiplicative? Assume we had some number which we could, let's say, yeah, let's just look at this summation, right? P1 plus P1 square until P1 power K1. Then we multiply that with 1 plus P2 square until P2 power K2, so on, 1 plus PR to the power KR. Now this is our, what do you say? Where was I? Yeah. Whereas if it was multiplicative, this is what the sigma of n would look like, right? You can accept that. Now if you look at this, I hope most of you are aware about like multinomial expansion, but then leave it. No, I'll just explain that. So if you look at this, if you pick any term from here, you can pick one term from each bracket. Like when you're multiplying together a polynomial, say 1 plus x and 2 plus y. What all do you get? You multiply 1 with 2, so you get 2. Then you multiply x with 2, you get 2x. Then you multiply x with y, you get xy. Then you multiply y with 1, you get y. Right? So when you expand a polynomial in general equation like this, the number of terms you get, you can find with a like combinatorial argument. It's the number of terms here into the number of terms here, right? That's the number of terms you will get. Now here, if you look at this, this is 1 plus k1 terms. This is 1 plus k2 terms. This is 1 plus k3 kr terms. So how many terms will you get when you multiply this, right? It will be tau n. So we know that the number of terms matches. Now we'll try to prove that it is exactly the terms we need. Now assume I took P1 from here and then I multiplied with everything else. If I change any one of them, it will correspond to a different different factor, divisor. It will correspond to a different divisor. Think about it once. Because like, if I hadn't taken P1 here, then I would have had P1 square or P1 cube. It's no longer the same number because everything else is co-prime. The factors obviously are unique. So we have tau n distinct terms, right? Now when I pick a term from here, every term will have P1 power something. That something is greater than equal to 0, less than equal to k1, which is what? Our acceptable range for a factor. So we have tau n distinct terms, which are all factors. Now think about it. If you have, say, 10 numbers, if you have 10 balls with numbers on it, and I took 10 of them and all of them have distinct numbers, I know all of them have distinct numbers, then I know that I have all the balls. Yes? So I have distinct terms and I know all the terms are factors and I have the exact number of them. So I have accounted for all the terms. It's a bit of an abstract argument, but then I hope you can agree with that. right? If you have any concerns at all with the proof, you can please put it in the chat. So with that, we proved that sigma n would be p power 1 plus p1 square, so on, p1 power k 1 into all that. Now again, this is gp. We can simplify this again. p1 to the power k1 plus 1 minus 1 by p minus 1 into p to the power k2 minus plus 1 minus 1 by p2 minus 1, so on, right? So we have a closed form solution for sigma also. Again, we'll do a sanity check as we did before. Sigma 12 will be 2 to the power 3 minus 1 by 1 into 3 minus 1 by 2. 3 minus 3 square minus 1 by 2. Yeah. So that's 8 minus 1, 7 into 9, 8 to 4, that's 28. So yeah, again, we had sigma n, we found closed form using a term counting method, right? And then, yeah, we have a closed form. Now, again, same reason as before, this is also multiplicative. If you want, you can try proving it yourself, but I'll just state it here because, like, see, this is one multiplicative term with one factor, another factor, another factor. It's the same thing that's happening here. If it's co-prime and you multiply, they'll just multiply normally. So then because of the closed form, we know that it's anti-multiplicative, right? Now, for the scope of this session, these two are basically like not incredibly useful. I just showed some like properties of number theoretic functions here. Like if you, but actually like this is related to like perfect numbers and all that, but we won't be covering that in this session. So it's fine, leave. Now we'll be moving on to a little bit more consequential functions. First, I want to discuss like a small theorem. Assume f and f are number theoretic functions. Right? Now, capital F, let capital F of n be defined as d divides n small f of d. Right? Simple definition. What I want to prove is that if f is anti-multiplicative, then capital F is also anti-multiplicative. I want you to look at that statement once and like think about it. Like let it sink. A sum of multiplicative functions is also multiplicative. In general, like if you consider like real functions, what is multiplicative? Like x is multiplicative, 1 by x is multiplicative, but x into 1, x plus 1 by x is clearly not multiplicative, right? So it should come as a bit of a surprise that some of multiplicative functions are multiplicative, right? So how are we going to prove this? So we have capital F of n is equal to d power n f of. What we want to prove is f of mn is equal to f of m f of n. That's what we want to prove, right? So we'll attack it from this side. This will be d divides n small f of d, and then d dash divides m f of, yeah. Now we just multiply them together. Get d divides n, d dash divides m, f of d, f of d dash. Now think about this argument carefully. M comma n are co-prime. So I will tell you all all choices, all d comma d1 are also coprime. Think about that argument once. Assume they weren't coprime. That means they share some divisor. If they share some divisor, m and n also share the divisor. But they don't, so d and d dash has to be coprime, right? Because they divide n and m respectively. So that means these two are coprime and we are multiplying them together. You can simply write them as d divides n, d dash divides m, and this is f of dd dash. Okay, so we have a sum of how many terms is this? We're going to count terms again. This is tau n terms. This is tau m terms. Since n comma n are coprime, tau mn is equal to tau m into n. So now look at this. We want to eventually show that this is equivalent to this. Yeah. We want to show this is eventually equivalent to this as in f of mn. Right? So how many terms are here? Here you have tau mn terms. Here also you have tau mn terms. That's promising. Now, how do we and here okay, fine. Now we want to prove that this runs over all the possible divisors of this thing mn. So assume some x divides mn. M and n are coprime. So either x completely divides m or x completely divides n, or can't be both, because then that would mean they're not coprime, right? If x completely divides m, then it would be here, and then m, yeah, that would be a factor here, and then you can multiply it with anything that divides n. That would be a factor of mn. It's a bit convoluted argument, but then yeah, if you have any confusions, please put it in the chat. What I want to say is, if we take a factor, all factors of m comma n, mn can be written as some factor of m into some factor of n. This is the crux of the argument I'm making here. I hope everyone can agree with that. If that is true, then this is basically that summation, and the inside part is basically that. So they're equal. Again, if you have any confusions with the argument, please put it in the chat. I know it's a bit complicated to follow. Okay, great. And you can see that this is true. Like before, when we defined tau n, we defined it as dn1. Here 1 is clearly a multiplicative function. 1 into 1 is always 1. GCD or not doesn't matter. Similarly, sigma n is also multiplicative, because see, d, this is identity. So like x into y is always equal to xy. Yeah. So you can see how this is, we already saw that this is a possible thing. Now we proved that it's true. Okay. Now we're going to the torsion function. Torsion. Okay. So this is the Euler torsion function phi of n, which is equal to number of coprimes, number of numbers coprime to n less than or equal to n. Okay, simple definition. So let's find phi 12. First we'll write down all the numbers less than 12, right? So 2 is not co-prime, 3 is not co-prime, 4 is not co-prime, 5 is, 6 is not, 7 is, 8 is not, 9 is not, 10 is not, and 12 is not. So we have 4 numbers. So 5 of 12 is 4. Okay, easy enough to accept. It's 4. Now I'll show you where this is used before like I derive properties of this. Yeah. So as Arjun explained to you, this is Fermat's little theorem, right? GCD theorem. Right? That's Fermat's little theorem. Now, what would you consider as a natural generalization of this? Like here we have the constraint that has to be only primes. One might think, why only primes? What if I take some like 15 or something? I put mod n. Then what do I do here to make it come 1? Obviously, GCD of an is 1. Euler proved this and he showed something actually what I feel is kind of remarkable. Phi n comes in the exponent. Like think about it for once. You're raising a number by the number of coprimes less than another number and it gives you remainder 1. I think that's kind of remarkable. I'm not going to prove it here. It's like maybe like 1-2 page proof. I will provide like an intuition for this though. We start with the Fermat little theorem. Like consider n equals 7, right? For Fermat little theorem, say I took 1. I kept multiplying 3 to it modulo 7. I kept multiplying 3. That will become 3. Then we'll go to 9. 9 is 2 again. 2 becomes 6. 6 will become 12. That's 5. 5 into 2 is 10. Wait 1 second. 1, 3, 2, 6, 4. That's 4. So we'll go to 5. And that will go back to 1. Right? In modulo 3, like 1, 3, 9, 27, 81, 729. 729. Not 729, 243. Yeah. Like this is just, if you take remainder with 7, you get a cycle. Alright? Now, this being a cycle is very important. Like what we're doing here is into 3, into 3, into 3, into 3, into 3, into 3. Now, think about this another like loop I'm going to make. If you take 0, add 1, 1, add 1, 2, add 1, 3, add 1, 4, add 1, 5, add 1, 0. This is say adding plus 1 in modulo 6, right? You can see how both of them look very similar. Now I want you to do this. Like consider, how would I say this? Mapping. Consider mapping from here to here. Like I make 1 go to 0, 3 go to 1, 2 go to 2, 4 go to 3, 5 go to 6, 3 to 6, 6 go to 3, 4 go to 4, and 5 go to 5. Right? Now consider this. I'm going to say that multiplying 3 here, like say I wanted to do 3 into 3. That is equivalent to doing 3 is here 1, 3, 3 is 1, 1 plus 1. That is my claim here. Doing 3 into 3 here is equivalent to doing 1 plus 1 here. Like according to this map. According to this map. Like we can check this also. This 3 into 3 gives you 2. 1 plus 1 gives you 2. 2 is mapped to 2. Like we can even do something like say I wanted to do 6 into 5. That is 30, which is equivalent to 2 modulo 7. 6 into 5. 6 is 3. 5 is 5. That's 8. Is again 2 modulo 6. Again, these are not the same 2's. I just happened to come to. But yeah, if you can see what I mean, if you get 2 here, means you get 2 here. If you get 1 here, means you get 3 here. Are you following my argument? Like, I am telling you that these two are equivalent. Any operations you do on these two are completely equivalent. Now consider this. When you are doing a power p minus 1, what are you doing? What you're basically doing is you're taking a into a into a into a into a, right? Many times. From my argument of equivalence, this is the same as f of a plus f of a plus f of a p minus 1 times. Agreed? So in the case of 7, we wanted to prove a power 6 is always equal to 1. Right? So consider this. F of a 6 times is equal to what mod 6? If you want, you can put it in the chat. What is 6 into something modulo 6? You just did congruence. More answers? Yes, it's 0. So it's 0. When you look at the map, what does 0 correspond to? 0 is 1. 0 is 1. So we with this like somewhat sketchy argument, you can see an intuition for why it becomes 1. Right? It forms a cycle. What you're doing when you multiply with 3 is you go like this 6 times and you eventually reach back here. When you're multiplying with say 2, you actually only need to go 3 times to reach back here. Right? Like 3 to the power 6 is 1 mod 7. But 2 to the power 3 itself is 1 mod 7. Or maybe 6 to the power 2 is 1 mod 7. With this like cycle, you can see why that happens. Basically, what you're doing is you're looping around, and when you get a multiplication, what do you say? When you move by like a what do you say? Not multiple. Forgot the word. Multiple of the chain length, you reach back in your original place. Like, yeah, that's obvious, right? Here, if I move 9 times, I'll obviously reach back here. Like I'm going around 3 times, I'm reaching back in my original place. That's basically what is happening when you're doing Fermat's little theorem. Now showing this for like non-prime numbers is a bit harder, but then there is a good analogy for that also. Consider 15, right? My n is equal to 15. And we are only considering a is co-prime. What I want to do is say I took 1 here, right? I multiplied by 2. Multiplied by 2. I'd get 2, 4, 8, and then back. Multiply by 2, multiply by 2, multiply by 2, multiply by 2. Right? I got 4 of them. Into the cycle. No, I don't think so. Fermat's little is like a good approximation, not approximation, is your best guess because it works for all cycles. I don't think it's possible to find for say like some specific number without calculating the whole thing. Okay, anyway, now this is only 4 of them, but if you write down the co-primes of 15, it's 1, 2, 4, 8, but then you also have 11, 7, 5, and 14. These are also co-prime to 15, right? Now, how do you get those? One idea would simply be like multiply 11 to all of them, right? So if you multiply 11 to all of these, you get 11. You get 11. Here 11, 22, 7, 14, 30. Right? These are all of them. Pay attention here. These are all of them. Again, if you multiply 11 again, they would just come back to the bottom. And also, like, if you multiply 2, they go like that. They come back. Now I drew this in a very specific manner. I drew this like a lattice. Because what I want you to see is, from the same type of argument as before, I want to equate this with another structure that looks like that. I hope you can see like immediately that it is the exact same thing. Like these are just vectors. You're adding 0, 1 if you multiply by 11. You're adding 1, 0 if you're multiplying by 2. Just let that sink in for a bit. See that they're actually the exact same thing. When you're multiplying by 11, I move like that. When you're multiplying by 2, I move like that. And if I do both of them enough times, I can create the entire lattice. And yeah, this is in mod 2, obviously, and this is in mod 4. Yeah. I want you to, like, for a minute or something, just look at this diagram. It's kind of bad diagram, but then I think you can see what I mean. You see like how the cycles are. They're the exact same cycles as before. Alright? In the case of like prime number, we technically did have a lattice, but then it was single dimensional. Here we have two dimensional. These look 3D, but yeah, this is like the same cycle. This is like two cycles we joined together. We're understanding the intuition here. Now, how would you prove that 5 of 15, 8, a power 8 is equal to 1 mod 15? How do you do that, right? So again, we're going to work with this analogy first and then convert it back to this, right? So any number would be represented as AB, where A is mod 4, B is mod 2. Multiplication here, in this analogy, multiplication is just addition. So adding will give you 8A, 8B, right? Normal vector addition. 0, 0 corresponds to 1. Now, if you look at this thing, you might say, why to go 8? You can do with 4 also, right? Like multiplying any number with 4 would give like both of these 0. You don't need to do it. In fact, if you actually try with 15, you'll find that 4 is enough. You don't need to go up to 8. You can't find this like a priori, but if you calculate for 15, you will see that this is in fact true. 4 is enough. You don't need 8. 8 will give you 8, we know. 4 is a better thing. Like this thing, important point about Fermat little and Euler's generalization of that. This a power some exponent is not the minimal exponent. It's just one of the exponents that work. Right? Like if I took 2x, that would also work. In this specific case, x by 2 also works. Okay, I realize I just dumped a lot of like information. So please ask if there are any doubts. Any doubts in this you can ask. This is just for like building intuition, because like if you don't get intuition from this, that's obviously my fault. So please put any doubts you need. I'll clarify. No, you can't find the minimal exponent. But we know like one of the, if there exists a minimal exponent, we know that it's a divisor of the exponent that the theorems give you. We know that for sure. Like this gave us 8 here. So possibilities are only 4, 2 and 1. Because like if it's minimal, then the only way you can get something else that gives you 1 is multiplying something with it. Like it's 1 power something. That is the only way. So if you know the full thing, you can technically brute force the minimal. But then yeah. Any other doubts? Like about the analogy and stuff. Okay. So I'm going to tell you a hole in this reasoning. It's not technically like I assumed that numbers like 2 and 11 exist for all numbers. I can't prove it to you. This is just for analogy. So I hope you can like vibe with this. Now, no. Important point. What I did here is actually group theory. It's a very like important, very omnipresent topic in like very advanced mathematics. I hope I have made you curious about that. Now you should go check it out after this session. It's extremely helpful. But this what I'm calling an analogy is actually group isomorphism. It's what's called a group isomorphism. Like I'm converting one operation into another operation. In more technical terms, that's called a group isomorphism. I hope I made you all like interested in this subject. So you should go check this out later. It's my favorite branch of mathematics, mostly. Anyway, back to number theory. We have our totient function, phi of p. Now we're going to start again like what we did for all the functions. We're going to start with prime numbers. Phi of p, how much is that? It's p minus 1. Like if you take 5, you have 1, 2, 3, 4, 5. So that's 4 of them, p minus 1. Right? No. Phi of p power k, how much would that be? If you say 25, you have to remove 5 and 25 from 25 itself. So that's yeah, p power k minus p power k minus 1. 5, 25, 10, 15, all that. All that you have to remove. If you count that, you'll get p power k minus p power k minus 1. Right? You can take p power k common here, and that is 1 minus 1 by p. And take p common here, 1 minus 1 by p. Right? Okay, now as a bonus question for your assignment, I want you to prove that phi of n is a multiplicative function, number theoretically multiplicative, of course. I want you to prove that phi of n is anti-multiplicative. Okay, that's a bonus question for your assignment paper, not because I'm too lazy to prove it. Anyway, yeah, so we're going to assume it's multiplicative and then we're going to derive a closed form. Like that's the opposite of what we did for the other things, I think. Yeah. Here we're going to assume multiplicativity, then derive closed form. Right? Okay. So yeah, if we know it's multiplicative, then n is equal to p1 power k1, p2 power k2, so on so on, pn power pr power kr. Right? We know it's multiplicative. Just write it as separately then. We know for prime powers, so that's just p1 power k1 into 1 minus p1, p2 power k2 into 1 minus p2, so on and so forth. So that is simply, this is just the prime factorization of n. This is n into 1 minus p1 into 1 minus p2, 1 minus 1 by p3. So yeah, simple enough. That's the closed form of phi. It's easy to see that it's multiplicative when you see the closed form, but we did it the other way around. So you will have to prove that in your assignment. It's the last question. Prove that this is multiplicative. Okay, I think that's all with the totient function. Anyone has question means please put in the chat. Next, we are going to consider the Mobius function. Okay, this is the last function I'm going to discuss for today. This is the Mobius function. Right? It has a bit more bigger definition, you can say, than the others we have discussed till now. Okay, I'm going to walk you through this definition again. So mu of n is 1 if n is equal to 1. Easy enough. Mu of n is 0 if any prime factor of it has like a square. If it's, okay, a good way to put this is, if the any factor of the number is a square, 5 of n is 0. Like say 4 or 12 or 48, they're all 0. 5 of them are 0. Square free numbers you call them. Yeah. Now, if you're not square free, that means all your prime factors are exponent 1. Obviously, right? Because square means any exponent greater than 1 would give you a factor as that prime squared. So here all your primes have factor less than 1. Then 5n is just minus 1 power r. Now this initially looks like a very vague definition. Like how did you even make this up? No motivation for this. Okay, so I'm going to put motivation for this now. Assume again you had some f of n defined as this. Okay, now say you are giving some, I don't know, Olympiad question or something. They give you the exact formula for f of n, as in you know every value of f of n. They ask you to find small f. How would you do that? One way would be like, say, consider f of 12 only again. F of 12 would be f of 1 plus, we wanted to find small f of 12. We want to know what is small f of 12, say. Capital F of 12 would be just f of 3 plus f of 4 plus f of 5. 1, 2, 3, 4, 6 plus f of 12. Capital F of then 6 would be f of 1, 2, 3, 6. And then 4 would be f of 1, 2, f of 3, f of 2, f of 1. Right? That would be f of 1, f of 3, f of 1, f of 2, and f of 1. Easy, right? Now, how would you find f of 12? Easy way would be like to cancel things out. One thing you can do is probably do, so you want this, you want to remove f of 6. The only way is to, so we do f of 12 minus f of 6. What do we have here? We'll have f of 4 plus f of 12. Yeah. 4, 1, 2, 3, 4. Now, how do you remove f of 4? Only happens in capital F of 4. So again, you have to subtract with the capital F of 4. So then you have f of 12 minus f of 6 minus f of 4. That would give you what? Small f of 12 minus f of 1 minus f of 2. Right? That's precisely capital F of 2. So what we get is small f of 12 is equal to capital F of 2 minus capital F of 4 minus capital F of 6 plus capital F of 12. Right? Easy enough. But then doing this is very irritating. Extremely irritating. Because you have to write down so many of them, you have to compute all of them. So I want to think of how can I make this look like a formula. Like since we are discussing under the Mobius function, obviously that's going to be a part of this. If you look at this, this looks almost like the divisors of 12, but then we are missing some. Right? So we can write that as 0 into f of 1 plus 1 into f of 2 plus minus 1, 0 into f of 3 plus minus 1 into f of 4 plus minus 1 into f of 6 plus 1 into f of 12. Right? Now, this is where insanely smart math people created this function, and then they simply did this. This is mu of 12, f of 1. This is mu of 6, f of 2. is mu of 4 f of 3. This is mu of 3 f of 4. This is mu of 2 f of 6. And this is mu of 1 f of 12. The thing is, like here, if you look at them, they all multiply to give n. So all of this work we can write simply as small f of n is equal to capital F of n into mu of n by d, and d divides n. All of that hard work we did. Yes, it is. I don't want to go there. It is related to convolution, but I don't want to go there. Yeah. So anyway, this is like all that hard work we did. You could have just gotten from this one formula. This is called the Mobius inversion formula. We're going to prove this for all functions now. Okay. Yeah. Cool. Now, initially, we're going to start with like another lemma type proof. Sigma d divides n phi of d. Easy. We want to find this, right? I want this is like a lemma for the total proof thing. I want to find this. How do I do that, right? Now, assume it was a okay. Yeah, this thing important point. I think you can see like easily that this is a multiplicative function, right? All the functions I'm discussing today are anti-multiplicative. Mu of n is multiplicative. Okay. So we can write this as f of n, right? F of n we can write as a sum of prime powers again. So that means we can break this into a product of summations. D divides p1 power k, d divides p2 power k, so on, right? And now we can just solve for prime powers. So what would this look like for prime powers? So mu of, assume this is p power k, mu of d. That would be mu of 1 plus mu of p plus mu of p square, on and on until mu of p power k, right? Now these all contain p square, they're all 0. You only have this. 1 is 1, and this is only one prime number, so it's minus 1. So it is 0, right? So now you see this, if k is greater than or equal to 1, you will get these two terms. Anything greater than 1 doesn't matter because it gets cancelled out. So if k is greater than or equal to 1, this is 0. If any one term in that summation is 0, all of them are 0. So we get that all the prime numbers power should be less than 1, right? So that means this is simply 1 if n is equal to 1, 0 otherwise. Easy enough, right? Any problems with this? Any problems with this derivation? Assuming nothing. Great. Now we want to prove the Mobius inversion formula. So we start by considering this f of n by d into mu of d. Yeah, I hope you can agree that these two are equal, because like you're just taking divisors now. This is like counting the divisors in reverse. The same thing as changing order of summation, not order of summation, changing like the direction of summation or whatever. Like here, if I'm summing like 1, 2, 4, 8, this is basically summing like 8, 4, 2, 1. Same thing, right? Okay. Now what we want to do is we can expand capital F. So we get this, and some c divides n by d, fd mu d, fc mu. Okay. Now here I'm going to make another important argument. The set of this I'm arguing this is completely equivalent to c divides n and d divides n by c. take a moment to like understand what this means, right? What I'm saying basically is, what this basically means is CD together divide n. So I'm just taking it the other way around, right? So you put that in the summation here. We can change the variables of integration without changing the inside thing. So you can make this is basically reversing order of integration, but it looks a bit more weirder when you're taking number theory summation. F of C mu of D. Now this f of c you can take outside. This is c n f c into d divides n by c mu d. This is basically the summation we found up. This is 0 if n by c is not 1. So our only non-zero term is n equal to c. So that means this summation goes, that's just c. It's a bit dirty work, but then we get that. Eventually what we get is f of n. Okay, you guys agree with this argument, right? Great. Okay, wonderful. Now now again we always sanity check your results. I'm going to do it 12 because 12 is easy. It has a lot of small factors. So we know that tau n is sigma d by. Now no one said you can't apply Mobius inversion here, so you should get this, right? D into mu of n by d, right? I mean not d, it's 1. Tau n for 1. Tau d, yeah. Seems legit, right? Now we try to see if this is true. Tau d for 1 would be 1, mu of n by d would be 0, and then tau 2 would be minus 1. No, tau 2 is 2 into something. Tau 3 is also 2 plus tau 4 is 3. Tau 6 is 4. Tau 12 is 6. Now this is mu of 12 by 2. Mu of 6 is 1. This is 0. Mu of 4. Mu of 12 by 3 is 4. That's 0. And then this is mu of 4. Mu of 3, that's minus 1. This is mu of 2, that's minus 1. This is again mu of 12, that's 0. So wait, no, this is mu of 1, that's 1. Yeah. So what we have here, this is 6. This is minus 7. 8 minus 7 equal to 1. Right? That works. Now we can try the same thing for sigma also. I feel like I shouldn't have. Whatever. Let's try for sigma also. Sigma n is d n d. Right. So then we should get that n is equal to d n sigma d mu of n by d. Right? Seems legit. Should work. So we'll start with say sigma 12. That's 28 into 1 minus plus 12 into minus 1 plus 7 into minus 1 plus plus 4 into 0 plus 2 into 1 and plus 1 into 0. Okay. So we have 28 minus 19 plus 2. That's plus 2. That is plus 2 or 3. 28 minus 19. This is 5 of sigma 2. Sigma 2 is 3. It's 3 into 1 plus 3. That is 31 minus 19, which is 12. So you can see the sanity check works. Now that is all the functions. This is the complete theory of number theory done. Like I'll take a short recap of what we did here. We had mu d, we had mu n, right? We found the inversion formula. Inversion formula. That's basically all we did. This inversion formula is very important. I mean, like not for you people, but then like it's very important for like advanced mathematics, out of OCAS mathematics and all. It's very important. It comes up in like Riemann zeta function and all. Out of scope of lecture, doesn't matter. So yeah, that is all the theory for now, and I'm going to be discussing one like short session on application of this number theory, right? Okay, now I'm going to ask you like a question. Say you have two people. This is Alice. That's Alice. That's Bob. They're very far away. Bob wants to send a secret message to Alice. But this is not secure channel. Like you're very far away. Like assume it's the internet or something. Maybe someone from some hacker. Yeah, this is a hacker. See, this is Eve. She wants that message. Right? Bob knows that simply sending the message is a bad idea. He doesn't want the attacker to get the message. Easy. Simple, right? How would you do that? That is the field of cryptography. This is heavily dependent on discrete maths and number theory in general. Heavily dependent. The reason you're secure over the internet, the reason you have this Google Meet, for instance, like your email ID, all your bank transactions, all of them is secure because of cryptography and number theory, right? I want to discuss the most probably the most influential cryptography, public key cryptography system there is. Now, what is public key cryptography system? I don't want to go too in depth into like the specific protocol and all, but then public key means that Alice has two keys. This is one is public, one is private. Anyone can get this public key, easy access, and they can encrypt a message. Encrypting message is basically like converting something that like information into something that looks random, basically random. Like doing like you could think of it like as if you're in a house, putting a lock on that house, right? The public key lets you put that lock. Only the private key can open it though. It's not like a normal lock. Needs two keys. Alice has both. Everyone else only has public key. So Bob has the public key. Eve has the public key. So if Bob sends a message, he uses this public key to encrypt it. Now the goal of the encryption is that Eve can't read it without the private key. The private key is never shared on the channel. So no one else knows the public key. I mean private key. But when this comes to Alice, she can use the public key and convert this back to the normal message. This is the encrypted message. Draw a lock. Yeah. Right? You can't read this. You read this, it'll be just gibberish. You won't understand anything. This, however, is the message that Bob wants to send. Now, how would you devise something like this, right? This is where RSA comes in. RSA is based on two facts, right? If you have a big number n, factorizing it is very, very I cannot put emphasis on it, very hard. Like maybe like a 256-bit number takes thousands of years to factorize. Very hard. Almost all of the older cryptography protocols was made based on this factor. Factorization is very hard, but finding and multiplying big primes, like massive primes, like hundreds and hundreds of bit long primes, is easy. This is easy. What we have here is doing this is easy, going back is hard. That is kind of what we need for a cryptographic system. I hope you can appreciate that. Now I will go into the specifics of why number theory comes in here. Now this is the RSA algorithm, somewhat simplified. You find P and Q, very big prime numbers. Right? These are very big prime numbers. You multiply them together to give n. Right? This n is public. It's not the public key. It's just something that, okay, n together with something else is the public key. One sec, I'll get to that. And then you pick a number e. Right? And on extra condition, it's co-prime to 5n. I hope you can see where this is going. So anyway, yeah, n5n, whatever. Yeah, you pick a large number e. This with n, this together with n forms your public key. This e comma n is your public key. Everyone will know this. Bob knows, Eve knows, everyone knows. Now, how will Bob encrypt a message? Bob has e. Bob has e, right? If he wants, first thing you do is your message, if it's in text or something, it's a text, image, whatever, it doesn't matter. Somehow convert it into a number, right? We'll call that number m. It represents the message. What Bob will do is calculate m power e in modulo n. Not n. That's equal to some c. Right? That is what Bob does. What Bob does is exponentiation in modulo. Right? Easy enough. And then this C is the encrypted message. So Bob sends C to Alice. Bob. Now assume Eve gets C, because like it's not a secure channel. You can steal messages. If she gets C, she wants a way to convert from C to M. She knows how to convert from M to C. The important part is to convert from C to M. Right? This is what she needs. She can do this. This is the hard part. How to do that? One way to do that, actually the only way to do that, is say you have like m power e. You have C. You don't know m, you know e. But finding like m from C comma e is not feasible. There's no other way other than brute force, basically. You want to convert C to m. How do you do that? You know C. What can you do? Assume you took C to the power d. If you took C to the power d, have we m power ed. Right? We want that to be equal to m. When does that happen? If you remember the Euler's theorem, this happens. This would happen if it's some k into phi n plus 1. Think about that. If it's k into phi n, then that's basically just 1 power k into m power 1, right? That is how you do it. But for finding this d, you need to know phi of n. But phi of n is n into 1 by 1 minus q, 1 by 1 minus q. That is pq minus p minus q plus 1, or n plus 1 minus p plus q. You need to know p plus q. Okay. But getting p plus q, there's only one way to get p plus q. You need to factorize n into p and q. That is what we said is hard, right? That's what we said is hard. From N to P and Q is hard. So Eve can't do anything. Or the only method of attack she has is to factorize a large number, which we already said is not feasible. But how can Alice read the message? Well, Alice knows everything. Alice knows P, Q, and all of that. So she can easily find D. Right? Using like Chinese remainder theorem or something, she can find D. She will simply do M, E, that's C. She'll simply do C to the power D. I'll automatically give her. That is how the RSA crypto system works. Right? So the same numbers that start with 1, 2, 3 is the reason your internet is secure today. That's the end of the session. That is all. Any questions you have, means please put in the chat, or else you can, I think, leave. You can leave. Sorry for taking like 40 minutes extra. But yeah, any questions you have, put in the chat, or else you're free to leave. People are very intelligent. I said you're free to leave. Yeah.